Hello students. Now today let us start with the salts of weak acid and weak base. Now here in this case, three situations will arise here. One is when Ka is greater than Kb. So as you all know, Ka is nothing but the acid dissociation constant and Kb means base dissociation constant. So when Ka is greater than Kb here, so you can write that this Ba, that is an acid, it will dissociate as B plus and A minus. So when these ions they undergo hydrolysis, you'll get this BOH plus HA, that is weak base and weak acid. So this is actually a salt Ba. It is a salt of weak acid and weak base here. So in case of the salts of weak acid and weak base, whether the resulting solution will be acidic, basic, or a neutral one, that can be decided by determining the or by knowing the values for Ka and Kb. Now, for example, you can take example that is ammonium fluoride here. The Ka value for this salt it is 7.2 into 10 raised to minus 4 and Kb equals to 1.8 into 10 raised to minus 5. So as you can see that Ka is greater than Kb. Now when you write the reaction for this particular example, that is ammonium radicals plus F minus means this NH4F, that is ammonium fluoride, it will dissociate as NH4 plus and F minus. So when these ions they undergo hydrolysis, it will give you ammonium hydroxide plus HF. So this reaction suggests that this is the salt of weak acid and weak base and weak acid. Okay. Now if this here, as I told that this Ka is greater than Kb. Now further, we can proceed. We'll go to the next slide. So here HF is stronger acid than NH4OH, which is a base. Now this NH4F, as I told that it will dissociate this way. Now NH4 plus H2O, it will give you NH4OH. Means I am writing the reaction separately for each of these ions. Ammonium, how it will undergo hydrolyze or how it will hydrolyze. NH4 plus it reacts with the water molecule to give NH4OH plus protonium ion is there. Now just to balance the reaction, we have to make this twice. Now F minus, it undergoes hydrolysis. It will give HF plus OH minus ion. So you can see here NH4 plus ion, that is ammonium ions, hydrolyzes to a slightly greater extent than fluoride ions. That is the reaction produces more protonium ion here than OH minus ion. So how can you say that it produces more protonium ion? By looking at the values for Ka, because the situation is like this, Ka is greater than Kb. So this suggests that there will be more production of protonium ion than this hydroxide ion. So NH4 plus ions are slightly stronger as acid than fluoride ions as a base. Therefore, this NH4F, that is ammonium fluoride salt, it is acidic in nature. So this production of more amount of this protonium ion, it will result in the, or rather it will hamper or it will dominate the pH of this ammonium fluoride solution. So it will produce a solution which will be acidic in nature. Now the next case, next we'll go to the next slide. The situation is like this. If Ka is less than Kb, means acid dissociation constant is less than base dissociation constant. Earlier we have seen that Ka was greater than Kb. Now exactly opposite thing. For example, ammonium cyanide. So it is the salt of HCN and NH4OH, isn't it? So here this HCN, it is a weak acid. So this HCN, it is a weak acid, and ammonium hydroxide, this is the weak base, because we are talking about the salts of weak acid and weak base. So now you can see here Ka for this is 4 into 10 raised to minus 10 and Kb is 1.8 into 10 raised to minus 5. So obviously this Kb is having greater value than this Ka. Now you can write the reaction for this also. NH4 plus and Cl minus undergoes hydrolysis, NH4OH and SCN is formed. You can write the separate reaction for each of these ions. Ammonium ion plus H2O, it will give NH4OH plus protonium ion is formed. And this cyanide ion, they react with water molecule to give this SCN and OH minus ion. Okay, so as this value for this Kb is greater than this Ka, so it suggests that cyanide ion hydrolyzes to a greater extent than this NH4 ion. And that is why this NH4CN, ammonium cyanide salt, it is basic in nature. So in short, that the values for this Ka and Kb will give you the information whether your solution will be acidic or basic in nature. Now the third thing may arise like next when Ka is equal to Kb. Now the example for this, the values for this Ka is 1.8 into 10 raised to minus 5 and Kb is also the same 1.8 into 10 raised to minus 5. The example for this you can take, that is ammonium acetate. Now you can write the reaction for this also, acetate ion, because this ammonium acetate, it dissociates as acetate plus ammonium ion and it hydrolyzes at CH3COH and NH4OH, which is the weak acid and weak base. Now we can write the reaction for this acetate ion separately and ammonium ion also. So you can see here there is a formation of OH minus ion and H3O plus ion. So since this Ka and Kb are having the same values, so whatever the extent of OH minus ions are formed here, it will be same as the formation of the protonium ion. So you can say that this ammonium acetate, it is the solution of this ammonium acetate, it will have the neutral pH. So in short, you can conclude that the values for Ka and Kb will decide whether your solution will be acidic, basic or neutral in nature. So this is true for the especially for the weak acid and weak base. This is not applicable, uh, rather this is especially for the weak acid and weak base, salts of weak acid and weak base. Now the next we can talk about next point, that is buffer solutions. Now before we proceed to the buffer solution, we have done these experiments in the laboratory, that is the inorganic qualitative analysis, where we do analyze the inorganic salt, in which we analyze basic radical and they are kept it, or they are divided into different groups, they are put in different groups. So for the first group, OS plus dilute HCl, if you get the precipitate, first group is present. Second, Orine solution plus dilute HCl plus H2S water, if there is a precipitation, then the second group is present. And the third thing, for the third A group, OS plus NH4Cl plus NH4OH. So this combination of this NH4OH and NH4Cl, this is what we call as the buffer solution. Means if the buffer solution is added to this, you'll get the precipitate. Then there is a presence of third A group, which comprises of aluminium Al3 plus radical. Now, this is the application of this buffer solution in inorganic qualitative analysis, which we perform in the laboratory. Now, what is actually this buffer solution is? So buffer solution is the solution which resists drastic change in pH when a small amount of strong acid or strong base or water is added to it. Means just to maintain the pH of the solution, we are adding this buffer solution, isn't it? Means this CH3COOH, CH3CONH4, this is the salt of weak acid and uh, weak acid and weak base here. So here you can see that this ammonium acetate, CH3COH in this case. So a solution containing, there are, just to maintain the pH of the solution. Now we proceed further. There are two types of buffer. One is acidic buffer and other one is the basic buffer solution. So acidic buffer, we'll just start with the acidic buffer solution. So this acidic buffer solution, it is the solution containing weak acid. Solution containing weak acid and its salt with strong base. It is called as the acidic buffer. So the best example for this, that is acetic acid, which is a weak acid, and its salt with the strong base, that is CH3CONA. So this salt is made up of weak acid and strong base. Here strong base is NaOH and weak acid is CH3COOH. So when these two things are combined together, this combination is called as an acidic buffer solution. Now this pH of this acidic buffer, it is given by the equation pKa plus log to the base 10 concentration of salt divided by concentration of acid. Whereas this pKa is equal to negative log of Ka. Ka is nothing but the dissociation constant of acid. So these equations you will be using for solving the numericals based on this. So acidic buffer is the combination of weak acid and its salt with the strong base. You just remember here. So we'll be doing this numericals later on. Now the next, that is the basic buffer solution. Now basic buffer solution, it is the solution containing weak base. You can see a weak base and its salt with strong acid. So this combination, it is called as the basic buffer solution. So the well-known basic buffer solution which is used in the laboratory, that is ammonium hydroxide and salt with strong acid, that is ammonium chloride. So this ammonium chloride is the salt of weak base and strong acid. Strong acid here it would be HCl and weak base, that is ammonium hydroxide. Okay, so ammonium hydroxide plus NH4Cl. This is called as the basic buffer solution. Now for this, since we are talking about the basic buffer, so we need to consider pOH. pOH will be equal to pKb plus log to the base 10 concentration of salt divided by concentration of the base. So pKb is equal to negative log of Kb. Kb is nothing but the base dissociation constant. So these equations, the earlier one, I'll go to the earlier slide. This equation number 1 and the equation number 2 also. This equation number 2, these are known as the Henderson-Hasselbalch equation. So you'll be solving the numericals based on these equations also. Now, this is about the acidic buffer, basic buffer, and what happens when the salts of weak acid and weak base, how does it affect the pH of the solution? There are three situations. Ka is greater than Kb, Ka is less than Kb, and Ka equals to Kb. Now we'll talk about the buffer action in the next lecture. Thank you.